is problem 19.
Okay. Okay, 19. Do you have it with you? I guess I don't have that in.
Yeah. I don't know how that works, but I couldn't get the problem. Do you want the picture?
I remember the picture for this one. Okay, so vectors number 19. We have a beam that makes an angle of 45 degrees with the horizontal. So this angle is 45. And if you draw a vertical line, there's a pin here that slides in a slot. And that slot makes an angle of 20 degrees with the vertical. And the length of the beam is 4 meters. And it asks first, what's a vector with a magnitude r that's perpendicular to that slot? And then the second question is, what's the vector if I call this point A and this point B? What's the vector to the point A from the point B? Okay, so for part A, I seem to remember this, like mentioning this sort of in passing last class. We haven't talked about the loads that joints apply to objects yet, but we're going to have one type of joint that we're going to deal with is a joint where there's a pin connected to a body that can slide freely in a slot. So it can slide freely in one direction. But if you tried to, so there's no resistance if you try to make this thing slide this way. But if you try to make it move that way, a force is going to be applied by the walls of that slot, perpendicular to the slot, that's going to keep it in the line. You know, you can't do that. You can't, it won't let you move it side to side. And so that question A is really asking us to represent the force that's applied to this beam in terms of a single variable. You know, an unknown force vector where you don't know anything about it has two unknown variables to represent it, an x component and a y component. But if we know the direction of that force, we can use that to come up with a unit vector, multiply it by an unknown magnitude, and then we'll have a vector with only one unknown, just that variable r. That's an idea we're going to use all the time. And so a problem like this is an important thing to make sense out of. Okay, well, I'm going to set it up like this. Here's the coordinate system. the main challenge of this problem is coming up with a unit vector in the correct direction. And so to come up with that unit vector, you know, there's two ways to come up with these unit vectors. One is if you know a vector in the same direction and you know its endpoints, you can do it that way. Or if you can come up with an angle, a counterclockwise angle from the positive x-axis to the vector you want, that's the other way, and then you just use cosine and sine. I'm going to start at the positive x-axis and keep hopping around to different reference points until I get to the one I want, because we know the angle from here to here, we know the angle from here to here, and then we're looking for something perpendicular to that. So let me draw this. So the first reference is from the positive x-axis to here. What's the angle from the x-axis, counterclockwise angle from the positive x-axis to the y-axis? That's 90. And then it's 20 degrees from positive y-axis to a vector pointing like up and to the left. So I'll draw this way, and we know that this angle is 20 degrees. And now it says we want a vector that's perpendicular to that blue vector. There, in 2 dimensions, there are 2 vectors perpendicular to any vector. In this case, there's one going that way and one going that way. Okay? Doesn't matter which one you choose. Let's choose this one, because it'll make the picture look less cluttered. In honor of Prince. Oh, and in honor of the Vikings' amazing finish. Did you just make a quiet woo sound? Yeah. Woo. Okay, so now we just have to add up all those angles. These are all counterclockwise motions. So the angle, we don't need to honor them that much. Okay, so theta is equal to, so you go counterclockwise 90 to get to the red vector. Go counterclockwise another 20 to get to the blue vector. Go counterclockwise another 90 to get to the purple vector. And so this angle is 110 plus 90, so 200 degrees. And so that vector is r times the cosine of 200, r times the sine of 200, and that gives you negative 0.940 r, negative 0.342 r. And what we've accomplished here that's useful in statics is now, instead of saying that this is an unknown force vector with unknown components rx and ry, having 2 variables we have to solve for, we've used what we know about the direction to represent it in terms of 1 variable r. And instead of 2 equations, we need 1 equation to solve that. Yep.
Where does that come from?
The purple one?
Yeah.
Because the problem says we want a vector perpendicular to this vector, perpendicular to the slot. And so this is one of 2 vectors perpendicular to the slot. I also could have gone 90 degrees back the other way, and we would have been looking for the opposite vector, and we would have just gotten positive 0.940
What
r.
about the 45?
The 45 doesn't matter in this part. It'll matter in the second part, in part B. Because all that matters here is the direction of the slot, and then 90 degrees from the slot. Any other questions about part A? That's definitely the harder, I think, of the two parts of that. And then part B, we want a vector from the wall pin to the slot pin. So we just want to come up with a vector that goes from that point B to the point A. One way to do that, and I'm just sort of citing these rules from the last lecture, so if you don't remember this stuff, you might want to skim back through the notes and remind yourself. But one way to do that is to put the origin at the starting point, and then you're trying to calculate the coordinates of the destination point. So we're trying to come up with those coordinates. And we know the length is 4. And we know this angle is 45 degrees. So if we're trying to find the angle theta that goes all the way from the positive x-axis to here, you can think of that as from the positive x-axis, you go 180 to get here, and then another 45 to get here. So that theta is 225. And so the vector is 4 times cosine of 225, 4 times sine of 225. And so you get 4 times, so that unit vector would be negative 0.7071, negative 0.7071. So 4 times that is 3.464. Is that right? Negative 3.464, negative 3.464. Anyways, it definitely is numbers in the way that those are numbers. And it's definitely negative because it's in the third quadrant. Yep. 2.83. 2.8. Oh, yeah. I'm thinking of 30 degrees. 2.83. Okay. Any questions about that one? Yes.
So when you go, the one you put at the origin is the one you're starting from, right?
Yeah, that's right. Or you can use whatever origin you want, calculate the coordinates of both, and then subtract. That's, yep. Any other questions? Yes. Okay. Any other questions on 19? Okay. 16. Okay, I'm happy as long as you guys keep not making me draw that 3-dimensional problem. Okay. So that's the one with the funny shaped object, the sort of J looking thing. And it tells you there's the center of mass. And it says we're using a coordinate system where the center of mass is the origin. And so there's a point here. Connected to a cable, and the cable connects to a wall. And then there's a point down here that's a pin joint. That connects to something else. And we're given some of these coordinates. So this point is 0.6, 0.4. That's where the cable connects to the body. Where the pin connects to the body is positive 0.05, negative 0.2. The cable has tension T. And first we want to know what's the force vector the cable applies to the object. Get by cable. And we know that this angle is 45 degrees. And then the second question is, what's the vector? Let me just label these points. And then, so let's call this point A, this point B, and this point C. And we want the vector from A to C. Okay, so for part A, we know that this force vector is going to be equal to the cable tension, that's going to be the magnitude of the force, times the unit vector in the right direction. The right direction for a force applied by a cable is always away from the body, parallel to the cable. So we know we're looking for a unit vector in the direction from B to C. There are two different ways to calculate a unit vector, and this is how I described it in the notes last time. One way is if you know the coordinates of those 2 points, you can subtract and then divide by the magnitude. And then the other way is it only works in 2D, and it only works well in 2D. But if you, instead of knowing those coordinates, you know an angle from the positive x-axis, then you can just use cosine and sine of the angle. Well, in this case, what we're given is the angle from the positive x-axis to the cable we want, the vector we want. So, because if this is the coordinate system, we want a unit vector in this direction. And so theta is just positive 45 degrees. People sure try that door a lot. Oh, really? Oh. So that unit vector is cosine of 45, sine of 45. And that's positive 0.7071, positive 0.7071. And so the force vector then is just the tension, that unknown magnitude t, times that unit vector. So I'll write it as 0.7071 t, 0.7071 t. In terms of significant figures, can anyone explain why for 45 degrees I go to 4 digits and for other angles I go to 3 decimal places? No, you can't, because there's no sensible reason. That's just what I do. I don't know why. Okay, so any questions about part A? And then for part B, now we want to come up with a vector that goes from that point A to that point C. So we want a vector that goes from here to here. That's equal to, by the rules of vector addition, that's equal to a vector that goes from here to here, plus a vector that goes from here to here. So that's how I'm going to calculate that. So if this is what we're trying to find, this is the vector from A to C. That's equal to the vector from A to B plus the vector from B to C. The vector from A to B, we can do that as a subtraction. That's 0.6, 0.4, minus 0.05, negative 0.2. And that's equal to 0.55, 0.6. And then a vector going from B to C, we can do that using the angle. We know the length of that cable is 0.5. And so this is going to be 0.5 cosine of 45, 0.5 sine of 45, and that's 0.3535, 0.3535. And so the vector from A to C is just this plus this. So 0.89035, 0.9535, and that can't be right. Oh yeah, that's right. Any questions about that? So part B was just like a vector addition problem, and you just had to come up with the components of the two vectors and then just add them. Yes? That was given in the problem that the length of the cable is 0.5. Any other questions about that one? That comes from adding. So this vector AC is equal to this vector plus this vector. And so that's this plus this. So 0.55 times 0.3535, I think is 0.9035. And then 0.6 plus 0.3535 is 0.9535. So it just came from adding this to this. Any other questions about that one? Any other homework questions? Yes. Mm-hmm. 21D. Um, D. Okay, so I'm just going to draw the thing. I'm not going to draw all the cables and stuff, but here's the object that all these forces are being applied to. And this is the point E. And this is the point G out here. That's a cable. And the wording says, what's the force? The force of the cable that goes from G to E. Okay. But I mean, that's just describing the cable. I mean, I could have just as easily called that the cable from E to G, right? So the order that I gave in defining the problem just said this is the cable we're talking about. But now if you talk about the force that that cable applies to this cross structure thing, the force that a cable applies to a body is always away from the body, like toward the center of the cable. So the vector, the unit vector that we want for this one is a unit vector going from E toward G. Okay. That's just a property of what cables do. Anything that pulls is that if you're pulling on something, the force vector is going away from the body. Any other questions about that one? So the direction of the force is this way, even though in the problem I described it as G to E. That's just the cable, not the force. Yep. It would be G minus E. So you always start, the first one is the final, and you're subtracting the initial. Yes? Oh, so that was your, no, I did not know that, but that's a good thing to know. Oh, I wish I had my phone. I'm going to fix all those things this semester. Where am I going to write that? Who wants to send me an email saying that? Yes, thank you. And I'll fix it. Any other homework questions? Okay. So now we're done talking about vectors. Although, you know, all of the kind of problems that you did on that vector assignment are going to come up over and over again in the statics assignments. Now we're moving on to our first statics topic, statics of particles. So what is a particle? Yep. Yeah, that's great. That's perfect. So, and let me clarify a little bit. So, yeah, it has mass. The fact that we're treating it as a particle doesn't change anything about its mass. But we treat it like it has no length dimensions. We treat it like it just exists at a single point. And so a lot of times people say that means that a particle has to be small, but a particle doesn't have to be small. If you're doing orbital mechanics, planetary motion, tracking, well, probably not true with satellites always, but you treat planets or stars even as particles because all you care about is the motion of the center of mass. You can't treat something as a particle if you care about what direction it's facing, if you care about its orientation. Okay? So if all you care about is like where I am at a given time, and you don't care whether I'm facing that wall at that location or facing this wall, then you can treat my motion as a particle motion. Okay? So particles are treated as having mass, but no length dimensions. And because they're treated as having no length dimensions, if you think about what orientation is, you know, the orientation is just really, it all relates to length dimensions. You can tell I'm facing this way because my eyes are facing that way and my butt's facing that way. But if my eyes and my butt are at the same place, you can't make that distinction, you know. So that was like philosophy. So if there's no length dimensions, you can't say anything about an object's orientation. And since there's no orientation, we're not going to use the moment equation at all. So therefore, we won't use the equation that says mnet is equal to 0. I don't know how I said this. Ma net. So for particle statics, we're just going to use the equation that says Fnet is equal to 0. How many equations does that give us? 2 equations if we're doing two-dimensional problems. Like if we're doing it in the xy plane, then this equation says the vector fx, fy is equal to 0. And 3 equations in 3D. When is a particle in static equilibrium? Well, one case occurs to everybody right away because, like in statics problems, we're usually dealing with, bridge type things that are just standing there. So one possibility is if the thing isn't moving at all. And by no motion, I mean no velocity. But it's also in static equilibrium if the velocity is constant. And you can use, excuse me, you can use all the same equations if the velocity is constant that you can if there's no velocity. That's because all that's required for to use that static equilibrium equation, since that equation comes from F equals ma, is zero acceleration. So I think there's a problem in your next homework assignment you're going to get where it says, do this problem for an object that's just sitting there on the ground, and then it's like, do the problem again for an object moving with a constant velocity. You do the problem the exact same way, get the exact same answers. Because the equation you're going to use requires that acceleration is zero, and that's true in both of those two cases. So now I want to talk about free body diagrams. I'll always abbreviate it FBDs. You need to draw a free body diagram for every application of Newton's second law or the moment equation. So you're going to draw a free body diagram every time you use Newton's second law or the rotational Newton's second law, the moment equation. I think it's easy to get into bad habits with free body diagrams because you start out with, you start out with problems that are simple. And with simple problems, it's not always super clear what the benefit of a free body diagram is. You can keep track of everything in your head. But as we get to more complicated problems, the benefit of a free body diagram becomes more clear. And I want you to have good habits by the time we get to that point. And so I'm going to take points off if you don't have free body diagrams when you use Newton's second law or the moment equation, just because I want you to get in that habit. It's an important part of this class. Sometimes people come to me and say stuff like, yeah, I don't do it that way. I do it this other way. I'm like, no, this is your second class. I've been doing this for 30 years or whatever. The way you do it is my way, or you lose points. Yes?
We have to draw on it's pushed on by X and gets pushed on in the opposite direction by negative X. If it's that simple.
Every time, yeah. Because that's to me, that's just part of building the habits, You won't have there will be no problems, no tests, no quizzes in this class where you need to worry about saving half a minute on a problem or what, you know what I mean? So just do it. It's good practice, good habit. I need to talk about what I want to see in free body diagrams. So here are the steps for drawing a free body diagram. So first you have to choose a body to isolate. And there's nothing particular about something being an object that's like an object. When I say choose a body to isolate, you could choose part of a car, or one wheel of a car, or 6 cars together with whatever ground they're touching. But it has to be a fully like enclosable. Am I really going to write enclosable? That is not a word. Fully enclosable 3D chunk of stuff. Second, draw a closed outline of the body. I guess I called it, yeah, of the body. And this outline should have no internal details drawn. And no outside objects. Reason for that is we're trying to be really clear to ourselves about where the boundaries are. So when I said like an enclosable 3D chunk of stuff, when you draw that free body diagram, you're imagining just shrink wrapping that thing, and all you care about is that shrink wrap surface. So let me give an example. So let's say that, so this is a car, and the car is sitting in the grass, and there's a Siamese cat on top of it. I'm Catman. And the car has windows and whatever, but that's not a free body diagram. So a free body diagram of the car looks like that. Okay? Not this. So what's wrong with that one? Yeah, the windows, the parts of the wheel, all that doesn't have anything to do with our shrink wrap surface. So we don't want that in there. All we're trying to do is make a distinction between what's in the club and what's out of the club. Yes? Mm-hmm.
If I write 10 in the center, consider that detail.
Yeah, you shouldn't do that. So if you're writing, so if you have a thing with 2 different weights in it, if you're isolating both of the weights together in one thing, then the person looking at it can tell from the layout which one is which. And if you're only isolating one of the 2, then you say somewhere above, I'm doing a free body diagram of the 10 kilogram mass. So you want to keep this just as simple as possible. All you want is the outline and the forces. Okay, so not this, because of internal details. Not this. because the grass is not being isolated. Not this. Because it's not clear what the boundary is. And then third, draw all the force vectors acting on the body. And how do you know when you've dealt with all the forces? Well, there are only two types of forces, two categories that forces can fall into. Field forces, I think in every problem we do in this class, field forces are just gravity, but you could also have magnetic fields, electric fields, that kind of stuff. And then once you've dealt with gravity, the only other way forces can arise is contact forces. So that means one force at each place the body boundary contacts the outside world, contacts the surroundings. And I think this is a helpful thing to sort of center yourself with when you get into complicated problems. So let's think about the car. So if this is the outline of the object, where are we going to draw force vectors? Well, the only field force is gravity, like in every other case in this class. So from the center, there'll be a weight force acting down. And now all we have to do is go mentally around the boundary and look for places where there's contact with the surroundings. Something here, and something here. So if we can figure out what the form is of the force here, here, and here, then we know we're done. We don't have to think anymore about are there possibly other forces. No, because it only contacts in 3 places. Okay. So these contact forces, you either know the direction or you don't. See, I guess I'll do this as let me write this as B1, if you don't know the direction, then you represent that force as a fully unknown force vector. And label it with a force variable. So for example, an unknown force vector would have a label like this on it. What that's saying is we have a force vector that's unknown with x and y components. And the location is here. You could also, a lot of people do it this way too. You could do it as Rx and Ry. Both mean the same thing. With a known direction, draw an arrow in the force's direction, and label it with a scalar variable. For example, so this says that we know the direction, it's this way. All we don't know is the magnitude, and the magnitude is represented by this scalar variable r. That doesn't have two components, it just has one. Or, mg or something like that. Any questions about that?
If we know the direction, should we also label it with like an angle? You know that.
Not on the free body diagram because we just want to keep it uncluttered, but you probably would have drawn a picture of that actual problem that would have the angle listed in there and stuff. That's not the kind of thing I would take points off for, but I think it's a good habit to not clutter up your free body diagram with anything but the outline and the forces. Yes?
Are we going to be dealing with things like coefficients of friction?
We're not in this class, and I'll sort of explain why that is pretty soon. Yes?
So for labeling each vector with a scalar variable, do we still have to adjust the length of the vectors? Because,
When you draw them?
yeah.
No, you don't have to do that. You can,
Either way.
yeah, make it all the same length or whatever, but and the variable associated with it is just meant to represent the length. Yeah. Any other questions? Okay, let me do a couple example problems. So we've already been talking a little bit about cable tensions. So let's say we have a wall here and a wall here and an object with a mass of 10 kilograms hanging by two cables. And let's say that the coordinates of this point are -2, 1. The coordinates of this point are +2, 1. And the coordinates at the center of mass of this object, that's the origin. We want to calculate those cable tensions. Okay, so the first thing we're going to do is draw a free body diagram of the mass. So there's the outline. And now we have to figure out what forces are acting on that object. There's a weight acting down. That's the only field force. So 10 kilograms times 9.81 is 98.1 newtons. And then there's a force vector with this known direction that I'll call T1, and a force vector with this known direction that I'll call T2. Those aren't the same cables, so like even though you might sort of glance at this and say like it's symmetric, those are going to be the same tensions, and they are. We're going to assume that they're different tensions. If you know two different cables, there's no reason that they would have to have the same tension, so we'll just leave it like this for now. Did I miss any forces? Nope. There's the field force, the weight force, and then go around looking for contact. There's contact at those two places. We knew how to represent the forces produced by those cables, so we know we're done. So now we have to calculate how to express the force vectors for these. That cable 1 on the left, that's equal to the magnitude T1 times a unit vector in this direction. The unit vector we're going to get by first coming up with a vector that goes to this point, -2, 1. Please ask questions if any of these steps don't make sense to you. Yes? So first what we're going to do, so there's two ways you can calculate unit vectors. One is with angles, and one is by subtracting coordinates. We're doing this subtracting coordinates, so first I'm going to come up with a vector that goes from here to here that isn't a unit vector, and then I'm going to divide by the magnitude. So U1 is equal to -2, 1 minus 0, 0. So -2, 1. The magnitude is -2 squared plus 1 squared square root, so root 5. And so the unit vector is -2 over root 5, 1 over root 5. And by the way, if you have a TI-89 or an Inspire, there's a function in your calculator called unit v that'll just, like if you plug in the vector -2, 1 and run the program unit v, it'll give you a unit vector in that direction. It's pretty useful. So that force is equal to -2 T1 over root 5 T1 over root 5. And then the force in that cable 2 is going to be equal to the tension T2 times a unit vector in that drawn direction. A vector that goes from the origin to the point 2, 1. You can get as 2, 1 minus 0. So the vector is 2, 1. The magnitude of that vector is square root of 5. So the unit vector is positive 2 over root 5, positive 1 over root 5. And so that force vector F2 is equal to positive 2t2 over root 5, positive t2 over root 5. Now we can go to Newton's second law. So Newton's second law says add up all of the forces acting. So add up the weight plus that force 1 plus that force 2. They have to add up to 0 if this thing isn't accelerating. So we have 0, negative 98.1. That's the weight force. Plus the force vector 2t1. What was that? Negative 2t1. Negative 2t1 over root 5, positive t1 over root 5, plus the vector 2t2 over root 5, positive t2 over root 5 is equal to zeros. And that gives two equations. The x equation says negative 2t1 over root 5 plus 2t2 over root 5 is equal to 0. And that tells us that t1 is equal to t2. And then the second equation says negative 98.1 plus t1 over root 5 plus t2 over root 5 is equal to 0. Substitute the first answer in that we got. We have here a system of two equations for two variables. So you can solve that. And what you get is T1 is equal to T2 is equal to 109.73 newtons. Any questions about that?
What is the 109?
What?
109.73.
That is the answer for the two variables we're trying to solve for, T1 and T2. So those are the cable tangents. Any other questions?
On that, do you care if we just jump from two equations to two variables to answer like that, or do you want us to show?
As far as like, I guess I don't really care. A lot of, and actually, in not too long, I'll talk about how to use your calculators to solve. Like, we're going to have a lot of big systems of equations, a lot bigger than 2 and 2. And I'll tell you how to solve that like numerically on your calculator in a really fast, easy way. So So a lot of times you're just going to solve these in your calculator. So I guess, no, I don't care. You don't have to show intermediate steps. Any other questions? Okay, let's do another example. So I remember being pretty young. I don't know, I would guess like 10 years old or something. And my dad, like, we were like working on a tree house or something, and he's like, oh yeah, pulleys, you know, they're one of the, I can't remember what it's called, like the 7 simple machines or something like that. And yeah, like pulleys decrease the amount of force that you need to apply, like to lift something or whatever. And that I never really thought about it, but it just sort of stuck in my head. And so I was sort of confused when I first talked about pulleys in a physics class, because a pulley doesn't, because you can use pulleys to, like, for example, you can rig up pulleys so you can hold up a thing that has a weight of 1,000 pounds by only applying 500 pounds of force to the cable. You can do that, and we're going to do a problem related to that. But the pulley itself doesn't do that. All a pulley does is change the direction of the force that a cable is applying. You know, like if you, let me draw a picture. If you have a pulley hanging here from the ceiling, and you have a mass of 1,000 pounds, if that's in static equilibrium, the only way that can be in static equilibrium is if you're applying 1,000 pounds to the other end of the cable. But with a very specific way of rigging up pulleys, you can get what's called pulley advantage. And so that's what the next example is. So it's not really a property of a pulley, it's a way you can use pulleys to make other things take up some of the force, essentially. So here we go. So let's say here's the ceiling. And let's say we have a weightless pulley connected to 100 kilogram mass. And then we have a pulley hanging from the ceiling like that. The way I have it drawn right now, this thing would not be in static equilibrium. It would be in free fall. So let's put a pulley, a cable like this. You understand the setup I'm trying to get at here? And so let's say we want to calculate that force T that has to be applied to the cable. What's T so that this mass is in static equilibrium? What does that mean if that mass is in static equilibrium? Not accelerating, so it could be moving. It would just have to be moving with a constant velocity, or it could be still. What do you think the answer is going to be? Anyone have a feel for that? It's going to be, yeah, 500 times G, because the force is 981 newtons, so it's going to cut it in half in this case. So let's see how to calculate that. First thing we have to do is a free body diagram. And I'm going to do a free body diagram of all the hanging stuff. And I'm also going to include the cable on the lower half of the pulley. In other words, all of this cable is included. Okay. And so a free body diagram looks like this. There's the hanging pulley. There's the mass. That's the outline. There's a weight force of 100 times 9.81. That's 981 newtons. And now just mentally go around the boundary. Where does the outside world, where do the surroundings touch that boundary? And let me do one more thing just to sort of make it clear what I'm including. So these little bat ears are the like little stumps of the cable that we're including. You follow what I mean? Okay, so where are the surroundings contacting that boundary? Yes, those stumps. And since all this cable is doing is going through the pulley, it's going to have the same tension here that it has anywhere else. So those have to be T. A weightless cable, which is what we're dealing with here, going through a frictionless pulley is the same tension anywhere along its length. So now we're done. We can go to Newton's second law and think about what forces are acting. There's the weight force. That's 0, negative 981. And then there's two forces acting in the positive y direction, 0t, 0t. Static equilibrium, so that equals zeros. And that gives two equations. The x equation says 0 equals 0, so that doesn't help. But the y equation says negative 981 plus 2t equals 0. So T is equal to 490.5 newtons. So in other words, you can hold up this weight of 981 newtons by only applying half of that force to the cable. That's pulley advantage. Doesn't come really specifically from the pulleys. It comes from the configuration of the pulleys. Any questions about that? Okay, I'll give you a couple of problems to do. Look on for Thursday, so just look on D2L for that. And see you Thursday.